Okay. In the last class, we were discussing how to make transmit filters. Essentially, the structure of the filter looks like a differential pair driving load resistors. And typically, when it's driving a transmission line, there are load resistors there are resistors at both ends of the transmission line. Okay. Effectively, that's what we have. And where to terminate the load terminating resistors is one of the things that we have to decide. Sometimes you have freedom over it and sometimes you don't. The available signal swing from this is I tail times R volts peak to peak. Okay. Because each of the load resistances is R by 2 effectively for the signal, and the peak to peak voltage will be I tail times R. The common mode voltage at this point depends on the terminating voltage here and also the total I tail times R. Okay. So what happens is, if you try to increase the amplitude of the signal, you can end up with the differential pair transistors in the triode region. Similarly, if you try to increase the number of taps in the equalizer or increase the magnitude of the taps, you will end up with the differential pair transistors in the triode region. Okay. And it also, not only that, it also depends on the value of Vx that you connect it to. Okay. We looked at several choices. So the first one was to AC couple the transmitter output. Now, if you AC couple the transmitter output with capacitors that are large enough so that their impedance is much smaller than R, then at the lowest frequency of interest, then the signal picture doesn't change, but the output common mode will be VDD minus I tail R by 2. Okay. And the signal swing, of course, is the same. And this is the peak to peak value. And the advantage of this technique is that the transmit output common mode is independent of the receiver. Okay. And the second one that you can do is to have Rx as a large common mode resistance. Okay. That means that this is connected to whatever voltage, but with a very large R, large enough that the effect of Vx on the transmitter output is negligible. Okay. So this the second one corresponds to the receiver looking like this. Differentially, it should always look like R, so that the transmission line is properly terminated. And this can be terminated by some high resistance to practically any voltage. If the resistance is high enough, then Vx does not have any effect on the transmitter output. Okay. And this is very much similar to the previous case, that VOCM is VDD minus I tail R by 2. Signal swing is I tail R, and the transmit output common mode is independent of the receiver. Okay. So as far as the transmitter is concerned, it is almost the same. The only difference is that now you don't have AC coupling, so you don't have attenuation at DC. This is a DC coupled termination. It's not visible. Okay, what else is the difference between the two? Is there any? Is there anything else? So the first technique will need large capacitors. Okay. The other difference is, this is a difference from the point of view of the receiver. In the first case, when you do AC coupling, the transmitter output common mode is independent of the receiver, and also the receiver input common mode is independent of the transmitter. Okay. The two can be set completely independently. Whereas in the second case, the receiver input common mode is directly the transmitter output common mode. Okay. When you don't have these blocking capacitors. So that is another consideration. This will be important for the design of the receiver itself. So in addition to this, one has large capacitors, and also the receiver input common mode voltage is independent of the transmitter. Okay. So all these things will come into picture when you start trying to design the receiver. So if you are constrained to some common mode voltage, that definitely reduces the degrees of freedom and the topologies that you can use. Otherwise, the two techniques are similar. What was the other alternative that we discussed? Tie VX to VDD. So this is just a pair of wires, okay, as far as the DC picture is concerned. So what about this? Is this what's the output common mode here? So in this case, it is VDD minus I tail R by 4. So both the common mode and the differential currents are terminated to VDD through resistances. So this will give you a higher common mode voltage. So that's actually the only virtue of this, that it takes the common mode higher. Okay. So for a given swing, all of them again have the same swing, I tail times R, peak to peak, but this has a larger common mode voltage. So that means that these transistors will be farther from triode region. So you can get a larger swing from something like this while still keeping the transistors in the saturation region. Okay. This assumes swing I tail R by 2. No, why? Yeah, that's okay. So the effective picture you have is this is R by 2, this is R by 2. Okay, and it's the same picture in all the cases, not just this, isn't it? And you can have either this one at VDD and this at VDD minus I tail R by 2, or the other way around. So the peak to peak swing is I tail times R. Okay, larger. This has a larger common mode voltage, so you can accommodate a larger swing. Is this point clear? Basically, you can have a larger I tail times R while keeping the transistors in saturation region, and I tail times R is just the swing. So you can have a larger swing. What is the problem with this? Is this this seems to be the best for transmitter design. What's a potential problem with this, or what's the flaw in the logic that I described so far? Actually, yeah, that is the big problem. So this VDD is with respect to this ground here, and you need to have basically the same ground and the same VDD. And one of the first things we discussed in this class was that you can't really have them to be exactly the same. So this is possible in some cases when you have two chips on the same board. They have a common ground plane, and there will be some errors, and it's okay to have some errors. So let's say this VDD is off by plus minus 100 millivolts. It is still better than when you did the AC coupling. Okay, but you certainly cannot use it when you are connecting like two boards that are far away with a cable. Okay, because there may not even be a common ground between the two signals. So this is possible only in a limited set of conditions where, and typically only when you have circuits on the same board. That is when you share the same ground plane and the same VDD. Okay. So you can't expect the same supply and ground on the transmit and receive sides. So it's useful only when the two are on the same board. Okay, so these are the different considerations, and typically you end up doing AC coupling because you may not know where the receiver is and you don't have a common reference between the receiver and the transmitter. Okay, so in summary, for the equalizer you have a number of differential pairs in parallel which go into terminating resistors, and both the number of taps or the magnitude of the total absolute magnitude sum of the taps is limited because you cannot have the transistors in triode region. Okay, so your swing will be limited. This is how this putting an equalizer on the transmit side can be a disadvantage, because you can't have very elaborate equalizers on the transmit side, mainly because of practical limitations. Okay. So, and we already covered the design of the equalizer. You have multiple taps and the tail current of each tap is proportional to the weight. Okay. So, you choose the tail current for the cursor and the load resistance. Let's say the load resistance maybe you have a degree of freedom, maybe you don't. If you have specified that the transmission line has to be terminated by its own impedance, you don't really have much freedom. You have to terminate it by that impedance. But you may deviate from that a little bit and you choose a certain current for the cursor tap based on the swing that you want. And after that you can choose the currents for the, you have to choose the currents for the other taps based on the ratios of other tap coefficients to the cursor. Now let's discuss one more thing, which is to make, which is to be able to make variable tap weights, right? Because we can have varying channels. At the very least, we will have different channels in different cases. So we have to set the tap weights to different values. Okay. So as we know, if you put an equalizer with a lot of high frequency boost to a channel that does not need equalization, you will actually create intersymbol interference. Okay. So let's say I keep this fixed and this current comes from some current mirror, and just for simplicity I will keep the cursor value to be fixed. Sometimes it can also vary because you may not want to reduce the total amount of signal that you are transmitting, total amplitude of the signal that you are transmitting, then you reduce everything, okay, reduce or increase everything. But let's say the cursor current is fixed and I want these two to be variable. What are the ways of doing this? How can I achieve variable coefficient weights? Oh, okay. Actually, that's a novel idea. Let's see. I'll just draw one tap here. Okay. So this is the cursor. You will do this. Okay. Where do you take the output from? So the idea clearly here is that the cursor current flows through both these resistors and this flows through this resistor alone, right? So where do you take the output? Huh? Output of this one. Yeah. So if you do this, yeah, definitely you can reduce the weight of the other tap. But then I want a number of different weights. What do I do? How? How will we vary the resistance? Yeah, one possibility is to have a MOS transistor, but then somehow you will have to vary. Firstly, the MOS transistor is not linear. That is one problem, because now you are passing the output of a linear equalizer through a nonlinear element, and that will introduce some distortions. So that is not necessarily allowed. Okay. But yeah, potentially you could vary these. You can realize these with MOS and vary them in a complementary fashion so that the total is the same or something. Okay. That's possible, but difficult, because you have to keep the MOS transistor in triode region for it to behave linearly. What else? How else can we vary the cursor weight, the coefficient weight? Thought we discussed this once already, right? Huh? Yeah, we can vary the currents. How do we do that? Current steering. So there are various ways of doing it. One possibility is to have multiple transistors here. You split a single transistor into multiple transistors. If you have all of them to be on, you get the maximum current flowing through this, and you can selectively turn some of them on and off. Okay, and to turn them on and off, you can do this. So I'll redraw this part of it here. To get a variable current source, one possibility is, okay, and let's say you have these, so then you can switch them on. So is this enough? Why do we need that? So it's actually not enough to just turn it off. You have to also connect this to ground, because the gate of a MOS transistor is a capacitor. So if you simply open this connection, that voltage will still be there on the gate. Okay. So it will still be supplying current. Okay, yeah, let's discuss different things. Okay, we can now go and discuss like various ways of making switch current sources. Okay, so firstly, one way is to do this. This is clear, right? So let's say this is B0, B0 bar, B1, B1 bar, and B2, B2 bar. So if depending on whether these logic levels are high or low, you either turn the current source on or off, and you connect all of the current sources in parallel, and you don't have to have 3, you can have a large number. Okay. So the total current here will be the number represented by B0, B1, B2, and times the current of each unit cell. Okay. What kind of switches will you use here? How do you make the switches? B0 bar will be NMOS. B0. How do you decide if you, firstly, you use MOS transistors as switches. How do you decide if you want to use NMOS or PMOS or both? Okay. So the control, let's say, is between V0 and VDD. Transmission gate. Why? Yeah, that's true. No, but do you need it? Yeah, of course you can put transmission gates everywhere, but do you really need it? That's the. So clearly the switches that are connected to ground will be NMOS. Okay. NMOS is very good at shorting something to ground. Okay. What about the other one? Can you use an NMOS or can you use a PMOS? Yeah, it actually depends on the value of this voltage. Okay. So this switch is NMOS. Now this can be NMOS. So if you tie it to VDD, it should turn on. That is the only issue, right? So if VDD is greater than 2VT plus VD sat, when it's on, this will be at VT plus VD sat, and this needs at least the threshold voltage across it. So if it's greater than 2VT plus VD sat, you can use this. Okay. Can you use a PMOS? So you can also use a PMOS if let's say the NMOS and PMOS thresholds happen to be equal, then you can certainly use this, right? Because you have the VGS of NMOS across this, and that's the same voltage that appears across the gate and source of the PMOS transistor. So if the threshold voltages of PMOS and NMOS are about equal, then you can certainly use a PMOS also. Okay. So it depends on these things, and so one of these has to be working, otherwise you will have to use a larger voltage than VDD to switch it. Okay. Why don't we go and put transmission gates everywhere? So you can try and put transmission gates everywhere you need a switch, but some cases it may not be useful. For instance, if you put a PMOS here, it will absolutely not do anything. Okay. Will it be on? When will it be on? So you can't really turn on a PMOS switch to ground, right, isn't it? Because if this is at ground, the gate has to be well below ground for this to turn on. So you can't use a PMOS switch here. So even if you use a transmission gate there, the transistor is not really doing anything, okay, under any condition. So the problem with using transmission gates is you will always end up having to supply both the true and the complement signals, and that can be a problem in some cases. So where you can get away with it, you try to get away with single transistor switches. Okay. So that is one thing. And the other idea that was suggested was to use a switch in the drain. Okay. Will you use an NMOS switch or a PMOS switch? PMOS switch. Why? So here, instead of using switches at the gates, you use switches at the drain. So if you open circuit the drain, the current source will be off. Is that correct? If I open the switch, what happens to this transistor? The VGS will still be there. Huh? How will it turn off? So we can't just open it, you are saying you have to put this to ground. Is that the case? So what happens when you open it is, it cannot draw a current through the open circuit. So the drain voltage keeps lowering and the current keeps lowering, and finally this voltage will fall to 0. So it is okay to just open this thing. Okay. So for instance, if you have a circuit like this, where the drain is open and you apply VGS, clearly the current is 0. And the current is 0 because this VDS becomes 0. So fine, we make these switches. How do we realize these switches? NMOS. Okay. So when you make a current source, this voltage can be as low as VDSAT. Okay. So if you use a PMOS switch here, this has to be at a voltage less than VDSAT minus VT, which can be negative. Okay. So you can't use a PMOS. So you have to use an NMOS switch at the drain. Now if you tie this to VDD, there will be a path here, and if you tie it to ground, this will become an open circuit. Is this okay? Okay, which one would you prefer? Switching at the gate or switching at the drain? Or is there something to choose? I mean, it's not it's an arbitrary choice. There is nothing to choose between the two. So at the drain there will be a voltage drop across this one. Is that what you're saying? Yeah. Which one? This voltage. Why? Switched off, fine. That's okay, right? No, when it's switched off, of course, that voltage can be anything. That is the idea of a switched off current source. Okay. What about when it's switched on? There will be a voltage drop here. What is the problem with it? The input? Yeah, basically the compliance of the current source. You are familiar with compliance, right? Compliance is just the voltage range of the current source. An ideal current source has infinite compliance. That is, for any voltage across it, it will give you the same current. But any real current source will have a finite range of voltages for which it will act like a current source. And in case of the MOSFET current source, it's limited by the saturation voltage of the transistor. Okay. Now you have the saturation voltage of this transistor and you have the additional voltage drop across this. So the total voltage is going to be more than VDSAT plus some V switch. So the compliance will be reduced. So that means that some of the other signal ranges or common mode ranges will be reduced. That's what happens when you increase VDSAT, right? So it will go, I mean, for smaller range of voltages, it will go into triode region. Okay, so you use a large transistor for the switch. You use a large switch to reduce the drop across the switch. Okay. So you can use a large switch, but then the drain to bulk capacitance of that switch will also be large. So the parasitic capacitances will increase. So does the drain to gate capacitance. So everything will increase. So that will have a bad effect. We will see what effect it has. Okay. If you have this, in our particular case, it is going to a differential pair. What is the effect of capacitance on this node? Do you know? Yeah, that is what happens. We will analyze that in detail. But you can't have a very large capacitance here. For clean switching, you should try to minimize this capacitance. Okay. We will see that in a moment, why that's the case. So if you use a large switch, the problem is that you will have a large parasitic capacitance and that will ruin the high frequency performance of this circuit. Okay. What does the switch drop depend on? V switch? What does it depend on? Yeah, it depends on current flowing, the aspect ratio, yeah, size, and the VGS it has. Okay. So you can't increase VGS, so you will have to increase the size. So we have two cases now, the switching at the gate and switching at the drain. Which one would you want to use? Gate. Why is that? Huh? Yeah, the main thing is when you connect a switch to the gate, there is no DC flowing through it. There is no DC drop. At least in longer channel technologies. In very short channel technologies, it turns out that there is a DC gate current. But at least in, let's say, 0.18 microns and above, there is no DC flowing through the gate. So you can use a minimum size switch or a really small size switch. Okay. So this is something that is never done. The only virtue of this is that you have a single control. You don't have to have complementary controls. So what else? We tried switching at the gate and the drain. Is there something left? Source. Can we put a switch at the source? Can we or can we not? So we have a diode connected transistor. What's that? Current mirror? Okay. So this will actually switch the current. So here you have to use an NMOS switch because it is connected to ground. And if you tie this to VDD, this will be like connecting a small resistor through this. Okay. But it is not a current mirror anymore. Okay. Meaning this current and this current are not exactly equal. How do we make them equal? So you can put the same switch here and connect it to VDD. Okay. And this can go between VDD and ground. So when it's connected to VDD, the two sides are similar, so you get accurate current mirroring. Okay. So is this better than switching at the drain or worse? Better. Why? Okay. So the capacitance that you see at this node will be the capacitance of this device. Is that the only thing? GMR times this capacitance. No, you will see the capacitance of this device directly. Okay, and you will see the capacitance of this attenuated. Okay. So that's fine. Is that the only compliance? Compliance reduces because you still have this voltage drop. Okay. So if you use the same transistors as before, for the main current mirror, you will have VD sat plus the voltage drop. But what happens to that voltage drop? Is it going to be different if I switch at the drain or the source? Why? It will be the same. The gate source voltage is different. So actually it is going to be different. Okay. So in one case you have this. Okay. And the gate source voltage here depends on what the current source is connected to. So this can be high, so you can have a large drop across this. So, whereas in the other case, what is the gate source voltage of the switch? The gate source voltage of the switch is VDD. So the resistance will be smaller, or equivalently you may use a smaller switch here, whereas you need to use a larger switch. Okay. So in general, switching at the source is better. In fact, you never want to switch at the drain. In general. Okay. Yeah. 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 So one of the, firstly, you are saying that this is now connected to ground, not to its own source, right? So VT of this NMOS is greater than the VT of this NMOS. Is that what you are saying? Yeah. 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 So that actually further worsens this, right? Sorry, not this one, this. So the VT of this is more than the VT of this one, isn't it? So this is M switch here and this is M switch here. So the VT of this transistor is more than the VT of this transistor. So this will be much worse. In fact, even without considering body effect, it's worse because VGS itself is smaller. In addition to that, the VT of this is more than the VT of this. So VGS minus VT for this, which is what determines the resistance of the MOSFET, is much worse. So you connect it to the source, and in any case you always design the switch so that the drop across the switch is negligible. Meaning, if you have, let's say, a VD sat of 150 millivolts, you don't want to make the drop across the switch comparable. Maybe you will make VC switch some 15 millivolts or something of that sort. Okay. So you always try to make it as small as possible. But so yeah, switching at the source, you can use a smaller switch than when you switch at the drain, and also the capacitance at the output of the current source is not determined by the size of the switch, it's determined mainly by the size of the current source itself. Okay. So those are the two advantages of this. But this switch will still be larger than when you switch at the gate. So finally our circuit looks something like this. If you want a differential pair with a variable tail current. I'll show multiple sources. This does not imply that the switching can be only at the gate. It can be anywhere. Okay. And drain, I think we have pretty much ruled out. So you can have switching at the source or the gate. If you switch at the source, you will have a larger switch size, and also there will be a drop across the switch. But the advantage is that you don't need complementary controls. And if you switch at the gate, you will have definitely a smaller switch size, and there is no compromise on the voltage compliance. Okay, there is no extra drop across the current source. When I say drop across the current source, I mean that its compliance is not reduced. And do we need complementary controls here? Okay, so we have something like this, and all of this is derived from a single, this bias is derived from a single transistor. Okay, and you turn them on and off. So firstly, do we need complementary controls when we are switching at the gate? Is it possible to do without complementary controls? In some cases, we need complementary controls. Is it yeah, if you use PMOS, that automatically interprets the control as a complement. So where do I use the PMOS? I use it here, and I use it here, and I can do this. Okay. So this way, when this is low, the NMOS is off, PMOS is on, it's on, and when it's high, the NMOS is on, so the current source is 0. Okay. What is the circuit? It's a CMOS inverter, right? So it's basically an inverter operating with, so normally when you think of it as CMOS inverter, this is the input, this is ground, VDD, and the output. So you operate a CMOS inverter with the required bias voltage as the supply. So it will either send out the supply, or it will send out ground. Okay. So that's all that's there to it. Of course, what is the condition for this to work? Actually, yeah, like we already evaluated it. The PMOS threshold voltage must be greater than, must be similar to the NMOS threshold voltage. Of course, VDD, this. Yeah.
But for the inverter to work, we need a threshold of NMOS plus the threshold of the PMOS.
Why do you need that? Why do you need VDD to be greater than the threshold of NMOS plus PMOS? It has to be greater than either one of them. It has to be greater than the larger one of them. Okay. So in this case, it means that the VGS of this device has to be greater than the threshold voltage of the PMOS transistor. Bulk to the source of the PMOS. What's that? Yeah. Yeah, you mean like to optimize it, you want to connect it here. Okay. Yeah, that's fine. So you don't want to further deteriorate the threshold voltage of the transistor, so you don't connect it to VDD. That's what you're saying. Yeah. But still, even the zero bias threshold voltage of the PMOS can be greater than that of the NMOS, in which case it may not work. Is this okay? So we can also switch at the gate without complementary controls. What is the size of these transistors? What do we need this size to be? Is there any restriction, or can we use minimum size devices? Of what? Not the mirror, not the size of these transistors. I am talking about the size of the switching transistors. Yeah, actually I didn't understand what you were saying. That's correct. That's the condition on these devices. Okay. I am talking about the switch. And normally the way you go about it is you design this current source, for instance, based on the signal that you need. Basically you want a differential pair, and the signals in the differential pair will dictate what size you will use for this and so on. Okay. You don't generally go and make this so that the switch will work properly. So typically the switch is the secondary one. Okay. You first make it so that this is the VD sat is low enough and the transistors has some VT. Okay. So you will get some VT plus VD sat at this point. Then you have to make a switch that works with that voltage. But that's not dependent on the size of this transistor. Okay. It's only the VT of this transistor that matters. For a switch, what is the length that you would use? Minimum. You'll always use minimum length, right? There's nothing, there's no reason why you would want to make the length of a switch more than the minimum size. What about the width? Would you make it the minimum? Why? What happens if you don't do it? Okay, so what is you want this size to be larger? Okay? You want WP be larger than WN, is that what you're saying? Why? What happens if I make them equal? No, let it be, right? What is the? Yeah, let it be. So actually also, see, this control, unlike in a regular PMOS inverter, this is connected to VDD and this will go between 0 and VDD. Okay. In this case, the supply terminal of the inverter is connected to this VGS, whereas the input still goes between 0 and VDD. So it will effectively switch off this transistor and switch it on also. There is no problem with it. Okay. The only thing that would govern the size of this is you have some capacitance here, and the rate of charge of this capacitance depends on the size of this transistor, because this acts like a resistance and it can rise up very slowly. So if there is a constraint on that, you may have to increase it from the minimum size. That's all. What's it? Yeah, maybe not, but it depends on the absolute value that you need. That's all. It may become an issue. If you have a very large transistor here, it may take a very long time to charge up. So okay, we'll stop here today. Still, we have, see, when you split up a single transistor into multiple transistors, the MOSFET width is the same, but you have to connect them with wires and so on. Okay. So the capacitance here will still be large because of all these wires that you have to route. So think of some ways in which you can vary the taps, but you don't have this extra overhead. Yeah, you can try and vary it continuously. There are some problems with it. We can discuss it afterwards. It is sometimes done, but it's not very desirable. Okay. The other thing is usually the adaptation engine works in digital. Okay, lots of times. Because it's a low frequency stuff, you implement the algorithm you want exactly in digital. So you prefer some digital control for the taps. Okay. So if you have an analog control here, you need a D2A converter to realize the digital control.